All right, so in the second video, I told you I would show you how to find, using a chi-squared independence test, whether the decisions that people are making are independent of the major that they're in. And by looking at this, isn't necessarily easy to tell. I mean, we know it's not perfectly independent, but it's hard to tell is this far enough off for us to think that it's not natural variation, that they really aren't independent, or are they slightly off and they're still essentially independent enough? All right, so let's answer the question. So to do that, I'm going to take this table and show you how the calculator gets us most of this. It'll be able to generate this, and it'll be able to get our chi-square statistic tested on a chi-square curve and give us a p-value and tell us the result. All right, so here's the test. So if we'd been in class, I would have wrote it on there, but here it is. So I did on my own off screen. All right, so remember, we're doing a hypothesis test, so we have our four parts that we need to do. The first part is to come up with the hypotheses. The good thing about chi-square tests is you can just write them out in words. So our null is, for chi-square test of independent, we're just going to assume independence. That's the normal, the quote-unquote assumed state of affairs. So what we're going to do is assume our null hypothesis is going to be that post-grad plans are independent of majors. So basically, majors not really having any effect on the post-grad plans. If that's not true, we'll go with our alternative that post-grad plans are not independent of major, basically signifying that major, for some reason, is having some effect. We don't know if major is the cause, but for some reason, different majors are making different postgraduate plans, all right? So that's what we're trying to find out. Now that we've defined our hypotheses, our next goal is to check our conditions to make sure we can perform the chi-squared test. So I'm just going to talk through these, so I didn't really write them out, but as always, you should put the reasons, so I'll just talk about them. The counted data condition, basically the original table had counts, so you can just say that, the table was given to us in counts, we have counted data, it's good. The other one's the expected cell frequency. We just need to make sure that every cell has at least 5. If you remember the table that I showed that had the expected values, which I will flash up real fast here. Remember this lovely thing. All these expected values are greater than 5. So that's what was necessary for that condition. So basically the expected cell counts are all way bigger than 5. Remember, since we're not trying to generalize this to the population, we don't need to check the other ones. But if I did want to generalize this to the whole college population, I'd want to check to make sure someone randomly picked these people and that the 10% condition was met, that they didn't pick more than 10% of the student body for this to work. All right, but since we're not doing that, we don't need to check them. I should also say, since the conditions are met, I'm going to perform a chi-square test of independence. But once again, I'm just talking through all of it, so you should say what you're going to do. So I'm going to do a chi-square test of independence. So here's where the calculator comes in handy, because the calculator, I'm going to show you how it gave me the chi-square test statistic. It ends up being way, way, way over here on the chi-square curve, meaning I get a very low p-value, which means I'm going to reject the null. How do I know all this? And how do I get the expected value table without having to do any calculation? So what you're going to do is go to your handy-dandy trusty calculator. You're going to go into a matrix. So you go to, it's so hard to show these on these videos, but it's up above this button, the x to the negative 1 button. So you hit second, then x to the negative 1, and you go to matrix. So if you go in there, if you took pre-calculus with me, we talked about how to do these matrices. You basically need to edit a matrix. So you're going to go to edit. And a matrix, if you didn't take pre-calc, didn't see a matrix, it's just an array of numbers. It's kind of like a table. So I'm going to hit edit, and I already did it because I needed to get all that information, but you're just going to enter, if you haven't done this before, you put in the number of rows and the number of columns. the table is 3 by 4. So you hit 3, enter, 4, enter. So I would do that. I already have it in there, but I hit 3, 4, and 3, enter, 4, enter. And you start entering, it'll make the matrix, if it's not the right size, when you put the 3 and 4, it'll make it so it has 12 entries. And then just enter in all the data. This is all of the data entered in from those tables. This is all you've got to do. As far as the preliminary work, the calculator will do the rest. So if you enter in this matrix, good news about a matrix is once you enter it, it automatically saves it. So after you enter everything, you would get down to, so to enter these, you just hit the number, hit enter, and it'll keep taking you across. You can also use the arrow to navigate. When you get to the last one, you don't have to save it or anything. Once it's in there, the calculator automatically remembers it. You're just going to quit out. Now you're going to run the chi-square test. So what you're going to do is go into stat and over to tests. So hopefully you know where the stat button is by now. And you're going to go down. And the one we did last time was called chi-square goodness of fit test. It was GOF. There's one above it that just says chi-square test. That covers the chi-square independence and chi-square homogeneity test. I'm not going over the homogeneity test, but I said it's the same exact calculation. So you could do either one this way. That's why it's given a generic name. So now all you have to do is if you entered the matrix into matrix A, which is what I did. Let's see if we can get this. There we go. The observed matrix is matrix A. You don't have to enter matrix B. If you just have matrix A in there, it will automatically make the expected value matrix, the thing I showed in the last video. So you just have A put in, B, it will calculate the expected matrix for you, and now you go down to calculate. So see if I can do this with one hand. Go down to calculate, hit enter, and now it's done all that work for me. It came up with the chi-square test statistic. It's the number 54.51. That's adding up all those deviances. So basically, what I showed in the last video, it took every cell, it subtracted the expected from the observed from the expected, it squared them, divided by the expected, and then added up all those numbers. It came up with the number 54.51. It then put that number on a chi-square curve with, as I mentioned before, 6 degrees of freedom, and came up with the p-value. So the p-value has that e to the negative 10 on it. So we'll talk about that in a moment. But there's my entire test, right? So I just entered a table, and there it is. It's done. If you want to see the expected values, like I calculate it all by hand, but if you want to go in and see them, you can go back to your matrix menu, and it will automatically put that matrix B in there. It was there before because I already ran this, but if you're doing it for the first time, you wouldn't see it until now. But if you go in, notice it automatically gets you all, those are all the expected values. So it makes the expected value matrix for you, which is really nice because it was a lot of work for me to do that by hand. Remember this guy. So the calculator came up with all that. And I say I made it by hand because before I knew that the calculator would do that, I would find this table and I would put it in. And when I made this lesson years ago, it was before I knew the calculator would actually do that for me. So I did do this one by hand, but basically you don't have to be stupid like I was. The calculator does it for you. If you just put in the original matrix, it'll make this expected matrix for you. All right. So notice that that's all in there. So that's how easy it is in the calculator. Now you just need to make the interpretation. For a curve of 6 degrees of freedom, 54 is a really big number. So the deviances are basically a lot. If this were independent, we don't expect this amount of deviance to be this high. So basically, the chance that if these were independent, for us to get the amount of deviance we see is extremely unlikely. In fact, how unlikely? I mentioned that it had the e to the negative 10. Make sure you know how to interpret that. It's 5.819 roughly times 10 to the negative 10. That means take this number and move the decimal point 10 to the left. That gives us 9 zeros in those numbers. So that's a super, super low p-value. This is the chance that if the data is actually independent, that we see the deviance we do. This is the chance that happens if it's independent. This is basically impossible. So I guess I should say it's impossible. It's astronomically unlikely. So our result is, since it's basically impossible or close to impossible to see this from independence, we're going to reject that null and say that they don't seem like they are independent. It's actually not independent. So what's your conclusion? Well, it's super low p-value, so I put due to very low p-value. We reject the null hypothesis. Make sure you put that in context. What's it mean to reject the null hypothesis? Well, rejecting it with this level of tiny p-value is basically, I said, strong evidence. There's strong evidence that postgraduate plans are not independent of majors. So basically, what did we finally answer was that does your major seem to affect your postgraduate plans? Well, they're not independent, so it seems like it does. People in different majors are making different decisions. Now, sure did take a long time to come up with that conclusion, but once you know how to do the procedure, it is actually very quick to do in a calculator. And that means anytime you want to test independence, it's not really that bad to do. So if we wanted to go back to that Titanic table, it would clearly show us that they weren't independent. But even things that are kind of close, we have a way of testing now. Do we think they're actually independent? So, for example, one of the more heated ways this gets used is, you could test things about people's race or people's gender or things like that. So if you think, someone of a certain gender or someone of a certain race is not being represented correctly, you could run the numbers, right? So if there's a little, maybe you run the numbers and a Hispanic people look like they're a little less represented, you could test to see if that's actually the case, right? Are there fewer Hispanic people through natural variation, or is it actually deviant enough for it to be where it looks like they're actually underrepresented? Now, clearly, once again, it's not causal. So if you tried something with races or genders or some heated topic like that nowadays, you have to be careful that, say, a race wasn't represented properly. It doesn't necessarily mean the person is racist who's doing it, but it might point to problems, right? So it doesn't prove the person's racist, but it might bring up questions to why is the data this way, and you might want to look more deeply into it. And when you look more deeply into it, you may find a good reason for it to be that way, or maybe there's a bad reason. Maybe the person is racist or sexist or whatever it is. But realize that those kinds of questions, political questions like that, can be answered using this. It can also be used on more boring things, not to rag on any particular subject, but I know these get used in, I believe it's AP biology, and I don't think it's necessarily as exciting to do it on, like plant samples or something, but this has lots of different uses. So anytime you're checking for independence, you can, remember, there's always going to be some natural variation in real life. You can basically see if that if the things are independent with a little bit of wiggle room, or if they're just too deviant. Like in this case, the deviation's too much. These guys are basically making different decisions. The proportions are not close enough to justify that the major doesn't matter. All right, well, that closes down the course. That's all the major topics, and we're basically running out of time here because school's going to end on the 12th. So I'm going to post this last lesson, and you'll have until the 12th to get all this done. Hopefully, if you've traveled this far with me and done these extra assignments, it's greatly appreciated. Thank you for your hard work. I can hopefully reward you with a really good grade for having done all the work that we've asked you to do. And like I said, even if you're not here listening to this video, I appreciate all the work all my students have done. I believe all of you are seniors and you're all graduating, so you've definitely earned it. Regardless of how the end of school went, it was a terrible thing, but you've done it. You're getting out of here. So too bad couldn't have been better, but guess what? You still got your whole life ahead of you. So there'll be lots of good times ahead. Basically, anytime there's a low point, things got to get better, right? So, like I said, I appreciate you doing all this and putting in whatever work you could, whatever you could do during this time, and hope your college experience goes way better than than this. So thanks again. Take care, and enjoy your graduation as much as you can. You guys have earned it. Take care.